Really powerful section right here. We're going to start our study of derivatives. In this section, we're going to talk about what a derivative is. We're going to talk about the main definition of the derivative. We're going to learn shortcuts later on, but even though we're going to learn tons of shortcuts, there are things out there where there are not shortcuts for. And even when we do proofs of certain things, we got to utilize this main definition there. So we'll show you, I want to show you the understanding behind it, like where this formula comes from. I'm going to explain where that comes from, talk about what a derivative is, and then we'll do one example and extensions of that using this main definition. And in future sections, we'll learn a bunch of shortcuts for these derivatives. But for now, I want you to know derivative is slope. Derivative is slope, rate of change, and rate of change is going to mean velocities, accelerations, all kinds of stuff. We're going to spend several chapters and sections on the derivative there. So this is just the beginning. Right now, you guys are such rookies because if I ask you to find the slope of a line, you need 2 points on that line, and you're going to use your basic slope formula right there. But see, right now, if I say, what's the slope of this curve? Well, now it's like we get stuck, right? Because the slope of that curve is not always the same. That slope of the curve is constantly changing, and that's what calculus does. When things are changing, calculus allows us to analyze certain things at instants, at moments like that, right? So what we could say right here, we can say like at this point here, we know that curve is like going up in that direction, right? So see how I made like a tangent line right there? A tangent line is a line that crosses the curve at one point in that vicinity. It might cross it again later on, but in that vicinity, it's going to cross it at one point. So what we define a derivative to be, if we could find the slope of that tangent, then right here, our curve is going downhill. So if I draw in another tangent line here, see how that tangent line and the curve are going in the same direction. And over here, if I draw in a tangent line here, that slope and the curve are going in the same direction there. So we define the slope of the curve to be the slope of the tangent line. They're the same at that instant, and that's what the derivative is. The derivative is the slope of the curve or the slope of the tangent line at that point. So we define the slope of the tangent line to be the slope of the curve. That's the derivative. So if I ever say find the derivative of a curve, find the slope of a curve, find the slope of the tangent line, that's all the same exact thing. And it's at that instant, at that instantaneous moment in time. That's our derivative right there. So eventually we'll do velocities, accelerations. If I say find the instantaneous velocity or just find the velocity, we want to know what's the derivative at that instant right there. Now, all we can say right here is that, hey, our slope is positive. There, our slope is negative. There, our slope is positive because our graph is going uphill, then downhill, then uphill. So we have positive and negative slopes, right? And we could also do a deeper analysis in the future right here. This graph levels off. It's a horizontal tangent line where the slope is equal to 0. So if the slope is equal to 0, the derivative is equal to 0. So in the future, when we do max and min problems on word problems or graphs, if I want to maximize or minimize something, that's going to eventually figure out where the derivative is equal to 0. So we got to know how to take the derivative of a lot of different things here in order to study calculus. Now, the nice thing is, look, you guys are such rookies because if I say what's the slope of that line, you need 2 points to find the slope of that line. But right here, we're talking about at 1 point, 1 point, 1 point. So we're going to get to more challenging curves than just a line. We could do any curve we want, and we just need the 1 point right there. And then we're actually going to do like a general formula to where we don't even have a point, and we're going to have a general formula that will allow us to find the curve at any point that we want here. So let me just share with you briefly the understanding. And then this is the notation we'll use for the first derivative of y prime, f prime of x, and dy dx. This notation over here will be a little bit more useful once we get to the word problems because it won't always be y's and x's, but that's how fast, the y's are changing with respect to x, and we'll talk about that as we go forward and we do certain word problems and we switch up those letters on you. What I want to share with you here, like if I take a point and my goal is to find the slope of the curve at that point, and we just talked about the slope of the curve is to find to be the slope of that pink tangent line right there. So if I can find the slope of that tangent line, that means that's going to be my slope of my curve. That's going to be the derivative at that point. Now, before we do any calculus at all, what we do know this slope formula. So we're going to start with our slope formula. But before I do, I got to get some points here. So I'm going to say at a general point x. So if this is x, if I wanted to find the y value, I would take whatever that is. I would plug it in for x into that equation there. So this y value here is going to be f of x. All right, so this is the point x comma f of x. Just pretend that was a 5. I would take the 5 and plug that into the equation. F of 5 would be my y value there. So that's the coordinates of that point. And here's what, so I don't know how to find the slope with just 1 point, but I do know how to find the slope with just 2 points. So here's what we're gonna do. I'm gonna draw in what we call, so this is the tangent line. That's ultimately what we want. I'm gonna draw in a point over here, and I'm gonna connect those dots right there. All right, now what I'm gonna define to be delta x, this delta x notation here. Delta x is the horizontal distance between 2 points. This is called a secant line where it crosses through a couple points there. It's not going in the same exact direction as the curve or as that pink line right there, but this point right here is gonna be x plus delta x, because delta x is the distance between those 2 points. So if I take x and I add on that distance, that's going to give me that x coordinate right there. So this coordinate is x plus delta x for the x value. And then I would take that, plug it into the original function. So the y value would be f of x plus delta x. Now what I want to do, I'm going to call this the secant line, that purple dotted line. And I want to find the slope of that secant line using my slope formula. So I'm just going to subtract the y's on the top, subtract the x's on the bottom. So if I subtract the y coordinates on the top, that will give us f of x plus delta x minus f of x. So I'm subtracting this y value minus that y value all over. Then we'll subtract the x's on the bottom. So this x value and that x value. So that'll be x plus delta x minus x. And then we see that these x's will cancel out. So the slope of the secant line is that, and you're starting to see this formula take shape. Now, this is not really calculus. All we did was algebra 1. I have 2 points. I did the slope between those 2 points, changing y over changing x right there, and that's the slope of that secant line. Now, here's where the calculus comes into play and the limit comes into place. So that's why we study limits first. You can't do derivatives or integrals without the limits, because in the main definition of the derivative integral, you're going to have that limit. Here's where the limit comes into play. So this is the slope of the secant line. Now, if I want the slope of that pink tangent line, I'm going to need to put that limit notation in front of there. Limit as delta x approaches 0. And let's talk about what that's actually doing here, because delta x is the horizontal distance between those 2 points on that secant line. So then what I'm going to do, I want that distance, that horizontal distance right there, to shrink to become 0. So this purple dotted secant line becomes that pink tangent line. That's what we ultimately want. Because think about it, if I take this point now and I drag that closer to this point, so I'm going to drag along the curve. Let's say I put a dot right there, and then I connected these dots, and I made another secant line, and I found the slope of that secant line using this formula. And then I'm going to take this dot, and I'm going to move it closer, and I'm going to do another secant line using my slope formula to find the slope of that line. And see what happens. All what this limit as delta x approaches 0 is doing for us is taking that slope of that point on the secant line on the curve, and is dragging it closer and closer and closer to where those points are right on top of each other. So we're just shrinking that distance between those 2 points on the secant line, because we can use a slope formula to find that slope. And when you shrink that distance to 0, that purple secant line becomes that pink tangent line, and that becomes a slope of the tangent line, which is the instantaneous slope at that point. That'll be the slope of the tangent line, which will be the slope of the curve. So that's where your main definition of your derivative comes from. And that's what we're going to be using in this section. Like I said, we're going to learn shortcuts later on, but right now we just need to practice this. And so let us go ahead and do one example with that, and we'll do some extensions here. So here's my main definition of derivative. And so I give you a function. I want to find the derivative here. So we're going to go f prime of x. And we're going to do the limit as delta x approaches 0. And we're going to go f of x plus delta x. So remember, if I give you f of 5, you take the 5, you plug that in place for x. If I say, what's f of Superman, you take the Superman and you plug that in place for the x's there. So if I say find f of x plus delta x, you got to take the x plus delta x and insert that in place for the x's. So we got the limit as delta x approaches 0. And I'm going to plug in the x plus delta x for all those x's. I remember to carry down that plus 1. That's my f of x plus delta x. And then we're going to subtract f of x, which means we're going to subtract the original function. Now, when you're subtracting the whole thing, you got to make sure you put that in parentheses, or you can just switch the signs and distribute the negative in your head and do that in one step. But remember to put that in parentheses and distribute that negative through, and that's all divided by that delta x. Now we know when we plug in the 0, we're getting 0 in the denominator, which is fine, but we're going to do our algebraic techniques that we learned with our limits, and we're going to multiply stuff out. Sometimes we'll have radicals in the problem. We'll do our conjugate approach. Sometimes we'll have complex fractions in the problem, or do our shortcut where we get rid of the complex fractions there. So all the techniques that we learned with our limit study, we're going to use in here. This is just now a limit problem that we already know how to do. So we're going to multiply this out. Now, the key common mistake on this one is when students do x plus delta x times x plus delta x, sometimes they mess that part up right there. So let's just be careful with that. So when I do that, that's going to be an x squared. And then you're going to go x times delta x plus another x times delta x. That's going to be a 2x delta x. A lot of times people forget that x, or they forget that delta x, or something's goofy with this term right here. So just be careful with that. And then you're going to go this times this. That'll be a delta x squared. But see, the 2 is in front of all of that. So I'm going to take that 2 and distribute it through. Remember that delta x is just like another variable, like an h, like a y. That's just another variable right there. So just treat that like you don't need to do like triangle squared x squared there. All right, then we'll distribute the -3 and distribute the negative here. Now, I know in the limit chapter, I kept having you write that limit notation every single time. I don't need you to do that here. What I want to see this notation at the beginning and the end of the problem. So that's what I want to see at the very first step. Show me that you know that main definition, throw that in there, and then you could do a bunch of algebra and then bring it back in at the end, because it's so important that we remember to take the limit at the end of the problem. Otherwise, you're not doing the calculus part of the problem, which is the big idea, right? With the understanding with the calculus. Now, what's going to happen here is everything's going to cancel out. The things that are left standing should have a delta x attached to it. If not, you did something wrong. So notice I got a 2x squared minus 2x squared plus 1 minus 1 minus 3x plus 3x. The things that are left standing all have a delta x attached to it. So I'm going to factor out a delta x. And then that will allow me to cancel out the delta x's. And now we have the limit as delta x approaches 0. I'm going to bring that back in at the end of this simplified version right here. And now we're going to take the 0, plug that in place for the delta x, and that will give us 4x minus 3. This is what my derivative is equal to, is 4x minus 3. All right, so this is your derivative equation. So let's make sure we understand what this is. The reason it has an x attached to it, right? Because we said derivative is slope. Derivative is slope. If you graph this equation, that's a quadratic. We know that it's a parabola. And so that's the reason why your derivative, your general formula for the derivative, has a variable in there, because the slope of this curve is going to depend upon where you are at along that curve. So if I want to know where I'm at this point, I take that x value, plug it in right here. If I want to know where I'm at this point, I take that x value and plug that in right there. And so you could literally go around that entire curve, just keep plugging in points where you're at of those x values, and it will give you the slope of the curve and, like, you know, the rate of change of that curve at that moment. So if I just say find the derivative, there we're good right there. Now let's go ahead and do a couple things with that. What I want to do now, I want to find the slope of the curve or the slope of the tangent line at x equals 1. And so that's the nice thing. You already did the hard work right here. So all you got to do, if you want to find the slope, you're plugging it into the derivative. So you're going to go, the slope at x equals 1 is the same thing as f prime of 1. So all you got to do is plug that 1 in place for x right there. So that's going to be 4 minus 3, which is equal to 1. If I say find the slope now at x equals 5, you already did the hardest part of this problem. All you got to do is take that 5. So if I want to find the slope, you're plugging it into the derivative. And so your slope at x equals 5 is the same thing as f prime of 5. And if you plug in 5 into the derivative equation, you're going to go 4 times 5, which is 20 minus 3, which is equal to 17. And so I kind of got the graph of our original function right here. So at x equals 1, we determined that the slope of the tangent line, or the slope of the curve, was equal to 1. So that was the rate of change. It went like up 1 over 1, up 1 over 1. Now x equals 5 is actually like way up here someplace. at x equals 5, it's actually the 0.5 comma 36, but then to see the slope is actually going to be steeper right there, and you figured out the slope of that tangent line, or the slope of the curve way up there is going a lot quicker. That slope is 17. And so that's what the derivative is going to give you. It's going to give you the slope at that particular point. There's something also called an alternate definition of the derivative, which it's a little bit different of a formula, and it'll give you the slope at a point there. But the downside to that is if you needed to find multiple ones, you got to do a different formula. You got to do work like this, like several different times right there. So I'll mention the alternate definition probably in class there, but this is our main definition that we got to practice. Now, something really important, another set of directions that we got to be able to do here is we got to be able to write the equation of a tangent line. And you're going to see these directions throughout all of our derivatives chapters, chapters 2, chapter 3, chapter 5. It's all going to be in there with the equation of the tangent line. And then the only difference is we're going to learn different ways of finding derivatives, and we're going to learn how to find derivatives of a lot of different functions and a lot of different shortcuts. But writing the equation of a tangent line, this right here is not the equation of the tangent line. All that is the slope of that line. But see, now I wanted to say, what is the equation of this line right here? What's the equation of this other line right here? That's what we'll work on here. So the derivative is not the equation of the tangent line. Those are two different things. The derivative just gives you the slope of that tangent line. So what I want to do, I want to write the equation of the tangent line at the x equals 1. All right, so at this point, our x value is equal to 1. If I want to find the y value, you got to plug it back into the original function. Okay, so at x equals 1, if I plug in 1 into the original function, that's going to give me, if I plug in 1 there and 1 there, that's going to give me 2 minus 3, which is -1, -1 plus 1 is going to be 0. So we just found that the point 1, 0 is on there. So when I'm writing the equation of tangent line, the reason I'm getting this point, because if you go back to your algebra days, if you're going to write the equation of any line, you need a point and you need a slope. So right there, I got a point. Sometimes they flat out give us that, and we don't need to find that. But if you're given the x value, you don't know the y value, you got to plug it into the original function to get that y value. Now that's your point right there. So if I say, hey, let's find the slope at x equals 1, that's why I chose this point, because we already have that over here. If I didn't have that yet, I would know that the slope at x equals 1 is the derivative at x equals 1. So when you want to find the slope of the tangent line, you plug the 1 into the derivative. That's going to give us 1 for our slope. So if our slope is 1, and then there's our point, there's our slope, you're going to use your point slope form. Y minus y1 equals m times x minus x1. We're going to use this a lot throughout the year. So you're just going to go y minus your y value equals your slope, which we found to be 1. And then you're going to go x minus your x value, which is 1. So this is just going to be y equals x minus 1. There's the equation of your tangent line. And so that's the equation. So the slope of this line is 1, but the equation is y equals x minus 1. All right, let's do it. Let's do it at x equals. So I'm going to still stick with the directions, write the equation of the tangent line. This time I'm going to do it at x equals 5. So at x equals 5, I need a point and a slope. So if you know the x value is 5, and you didn't know the y value yet, which we don't know, I got to take the 5, plug it in for x into the original function. So I'll go 5 to that's 25 times 2, which is 50. 50 minus 15 is 35. 35 plus 1, that gives me my y value is 36. So they may give us that, and we don't have to do that. But if you don't know the y value, plug it into the original function. And then your slope at x equals 5, that's when you plug it into the derivative. And that's why I already did that one with you over here. So you just see how we're doing something different when you write the equation of the tangent line. So once you have your slope or your derivative at that point, and then you have that point, if I say, what's the equation? So the slope of this tangent line is the 17. And now we want to know what's the equation of that tangent line. So I'm just going to do the point slope form. So I'll go y minus my y value equals my slope, and I'll go x minus my x value. Now what we're going to accept this year is we're just going to be able to leave that in point slope form. If we're doing the AP test and it's on the free response, they will accept point slope form. I guess when I change it, you know, the reason only reason I would need to change it if I'm using it for something, I might want to have that slope intercept form, or if it's a multiple choice situation and I see all the choices are y equals something, then you're going to use common sense and you're going to make sure you just put that in slope intercept form. The reason the tangent line is so important, because if you take like more involved curves, let's say we got this crazy curve going on with a crazier equation. And let's say we knew what the equation of this tangent line is. And what we'll use later on is something called tangent line approximations. And so notice that in this vicinity, all the points on the curve are close to, like if we zoomed in right there, all the points on the curve are nearby the points on the tangent line. So sometimes if we have a real simple tangent line, which is just x to the first degree equation, linear equation, it's going to be easier to plug stuff into the tangent line than it is to the more complicated curve right there. So we'll use a tangent line for certain things there. But the biggest thing is make sure we're practicing the main definition of the derivative. And then when you get to this step, we'll have the limit notation at the beginning and end. And then when we get here, you're going to have to remember all of your limit techniques from our limit chapter, all the complex fractions, the conjugates, the multiplying stuff out, the factoring and canceling, and work with that. And then get this general thing for your derivative. And then once you have your derivative, you want to find the slope. You just plug stuff into the derivative. If you want the equation of the tangent line, you plug it into the derivative to get the slope. And then you could do your point slope form and go from there.